Sometimes when we're doing calculations to calculate the equilibrium concentrations using ice tables, we can't simplify and take the square root of both sides. So they can get a little bit tricky, but I'm going to give you two strategies to solve them. First example, dinitrogen tetroxide decomposes into nitrogen dioxide. So you start just like any other question and write a balanced chemical equation. So we have N2O4 decomposing into 2NO2 gas. All right. So the K value is 4.50. And the initial concentration of N2O4 is 0.5. So 0.50, and this is initial. We have no nitrogen dioxide. It goes through a change, minus X plus 2X, equilibrium 0.5 minus X and 2X. All right, so our K expression is equal to concentration of NO2, second order, over N2O4. So we're going to substitute in our values. We have 2x all squared over 0.5 minus x is equal to 4.5. Now, in this question, we can't take the square root of both sides because the denominator has only one term in it. It's not squared. So what we have to do is expand the top and bring all the terms together and see what we have. So we have 4.50 times 0.5 minus x is equal to 4x squared. So if we move everything together and simplify this side, we have 4x squared minus 2.25 plus 4.50x. So I've expanded the items on the left and moved everything so it's all on the same side. So we have no choice in this question. We have to use the quadratic equation. So x is going to be equal to negative b plus or minus b squared minus 4ac all over 2a. So b is 4.5. So negative 4.5 plus or minus 4.5 squared minus 4, a is 4, and c is minus 2.25 all over 2 times 4. So once you substitute those values into your calculator and do the math, you're going to have two roots. X is going to be equal to either 0.375, and that's moles per liter, or X is going to be equal to minus 1.50 moles per liter. Now, we cannot have a negative quantity. So we cannot use this negative root. We have to use this one. So now, just going to move this up. Substitute in concentration at equilibrium of N2O4 is 0.5 minus 0.375 moles per liter. X, so 0.125 moles per liter is our concentration of N2O4, dinitrogen tetroxide, but we can only have 2 sig figs, so 0.12 moles per liter, and then 2x is our equilibrium concentration of nitrogen dioxide. So 2 times 0.375, 0.75 moles per liter. So you can use the quadratic equation for some of the tricky ones, but if we don't have to, if there's another alternative method for solving, then we will use that. And guess what? There is. Now the only problem is with this solution, this alternative solution is that you have to have a very small K constant. So your K value has to be times 10 to the negative 5 or smaller in order to do the next method. Otherwise, you're stuck using the quadratic. All right, so nitrogen and oxygen gases react to produce nitrogen dioxide. We have 0.085 moles of nitrogen, 0.035 moles of oxygen placed in a 1.5 liter container. What are the equilibrium concentrations? Okay, so you have to figure out the concentrations first. So 0.85 moles divided by 1.5 liters and 0.035 moles divided by 1.5 liters. We're going to set up an ice table. We have 0.0567 moles per liter of nitrogen and 0.0233 moles per liter of oxygen, and we have 0 product because this is the start. So minus X for nitrogen, minus 2X for oxygen, and plus 2X for NO2. So at equilibrium for nitrogen, we have 0.0567 minus X, oxygen 0.0233 minus 2X, and nitrogen is just 2X. Sorry, nitrogen dioxide is 2X. Okay. Now let's put those into our K expression. So K is going to be equal to the concentration of nitrogen dioxide to the second order over nitrogen to the first order, oxygen to the second order. All right, so always write out your K expression before putting in the numbers, and then put your numbers in. So we know we have 4.2 times 10 to the negative 8 is equal to 2x squared over 0.0567 minus x times 0.0233 minus 2x squared. Okay, we cannot take the square root of both sides of this, but we have something in our pocket called the 1000 rule. And it's not because chemists are lazy, it's because we're efficient and we don't like using the quadratic equation if we can get away with it. So this is a great assumption if a certain rule is applied. So the 1000 rule says that if your initial concentration, that's an I, divided by your K value is greater than 1000, you can make the assumption that anything plus or minus x will be just the number. For instance, 0.0567 minus x is 0.0567. So you'd be able to say that 0.0233 minus 2x would be equal to 0.0233. So you have to put this over to the side. So our initial concentration, we'll pick the biggest one, 0.0567 divided by our K, 4.2 times 10 to the negative 8. If this number is bigger than 1000, we can make this assumption. And this is equal to 1.35 times 10 to the 6. So this is indeed larger than 1000. So we're going to simplify that way. So 4.2 times 10 to the negative 8 is equal to 2x all squared over 0.0567 times 0.0233 squared. So what that's saying is that x is so small that it's not really going to change these values. It's not really going to change these values, so it's insignificant. So now we can simplify. So this is 4x squared over 3.078 times 10 to the negative 5. I'll just make this a bit smaller because I'm running out of room. Okay, so now simplify. 4.2 times 10 to the negative 8 times 3.078 times 10 to the negative 5 is equal to 1.29 times 10 to the negative 12. This is equal to 4x squared. Divide both sides by 4, which gives us x squared is equal to a value, and then you take the square root. So you're solving for x. So x is going to be equal to 5.6 9 times 10 to the negative 7 moles per liter. So that's really, really small. So now take that value away from the E line in our equilibrium table, and we will have our equilibrium concentrations. So the concentration of N2 is equal to 0.0567 minus X, which is approximately 0.0567. Concentration of oxygen is equal to 0.0233, and the concentration of nitrogen dioxide at equilibrium is 2 times X, so that is equal to 1.14 times 10 to the negative 6 moles per liter. So very little nitrogen dioxide is formed, but that's to be expected given that our K is so small. Our K is so small that the equilibrium lies to the left with the reactants. So very little products form. But now we know at equilibrium what the concentrations will be. So if you can, always use the second method and simplify using the 1000 rule. It really does save you some math. If not, use the quadratic formula.